we're at the last problem for practice exam for the exam number 2. So problem 4, I know you're fatigued, but don't fracture just yet. I can't get enough of these puns. So in this problem, we're going to be dealing with basically fracture mechanics, fatigue, and kind of all those different kind of phenomena. So just to kind of remind ourselves before we get going, let me here. We have kind of 3 equations, or 3 real kind of important equations for fracture. So we have our Griffith, where stress at fracture is equal to square root 2 gamma E divided by pi a cube. We also, Griffith is for very, very brittle fracture, so brittle. And this is kind of talking about, so for glasses, kind of those types of materials. We also have our Orwan criteria, which is very, very similar. So we have our stress at fracture is equal to square root of our Young's modulus E times G sub C, which is this kind of strain energy release rate divided by, again, pi A. And then we have our fracture toughness. Which is going to be equal to K sub C, depending on what type of loading state we're in. F, which is constant, set that equal to 1. Stress, square root pi A. So, just received an email. So those are kind of the 3 equations that we're going to use to kind of figure out, okay, what's the stress at fracture? What is our kind of critical crack size that will lead us to fracture, and what stress is required for fracture as well. So we are going to get into our Paris law and fatigue in just a second, but let's kind of read this problem now. TV series, The Office, Jim would often prank his coworker Dwight. Today, when Dwight went to sit down in his office chair, it broke. Dwight was furious, convinced it was Jim sabotaged his chair. Dwight actually obtained his degree in material science, Santa Barbara, blah, blah, blah. I decided to investigate. So when Dwight sits down on his aluminum chair, so aluminum, there's a square seat with a side length of 23 inches. So he exerts a force of 784 newtons, and he removes the same force when sitting up. Dwight is careful not to touch the sides of the chair when sitting. Aluminum chairs will typically fracture at a maximum normal strains of 0.12. For aluminum, K1C, excuse me, I made a mistake, I told you not to. K1C is going to equal to 29 megapascal meter half. So let's go ahead and let's look down a little bit further on the problem. Write out the stress tensor for this problem. What is rotation required to be maximum principal normal stress state? What about maximum shear? Write out the tensor quantitatively as well. So let's go ahead and start to kind of break down this problem. So right now we're just doing with our general linear elastic problem setup. So I have a chair that is basically kind of this, basically it says it's a square, rectangular square. So I have my cube. So let me draw my cube here. So I have my cube like this. I have my coordinate system here, 1, 2, 3, and I'm pushing down. There's a stress applied here, and that is it. That is the only kind of applied stress here. And when we push down, what's going to happen in this normal stress sigma 3, that material is going to want to expand in this direction, and it's going to want to expand into the board and out of the board. There is no constraint here, and this statement that he's careful not to touch the sides of this chair when sitting means we don't have any shear stresses as well. So let's go ahead and start to write out our stress tensor for this problem. So nothing to deal with stress tensor, and we'll actually do the strain tensor as well. So I'm cheating already, so I'm going to have my T matrix already set up. T matrix form, because might have to use that in just a second. So let's evaluate once this runs, mathematics thinking, excellent. So I've got my stress tensor, or my T matrix. So I have in my stress tensor, will I have stress in the 1, 1 direction? No, there's no constraints, right? I won't have stress in the 2, 2 directions either. And because, again, that statement that Dwight was careful not to kind of touch the sides of the chair, there's going to be no shear as well in this material. So your stress tensor is just your uniaxial. This is the only time you could use Hooke's law. Or maybe not the only time, but one of the few problems when you'll use it. So sig 3, 3. That is my stress tensor. So let's look at stress, matrix form. There we go. What is my strain tensor? So again, if I have no shear stresses, I know I'm going to have no shear strain. But will there be strain in this direction here, in the 1, 1? Yes, it's unconstrained. When I push down due to Poisson's ratio, that material is going to expand in that direction. So I'll have E11, 0, 0, 0. I'll also have E22, 2, and I will have, and I will have 0, 0, 0. I will have E33. Excellent. So let's look at strain, matrix form, and there we go. So let's start to figure out these values quantitatively before we kind of get into anything else. Let's just kind of solve this equation. So we know that E11 is going to be equal to 1 over E, or 1 over Y, where, let's start to define these values. So we said that we're working with aluminum. So you could approximate that as like 100 gigapascals for your Young's modulus, but I know that aluminum has a Young's modulus of 69 gigapascals. So 69 times 10 to the 9th. That's a good value to kind of remember. My new value is going to be equal to 0.3 because I'm working with a metal. And yeah, so let's start to kind of think. There's one more value that we could, do we know what is going to be the strain in the 3, 3 direction? No, right? There's really no value that kind of tells us like what, there's no kind of expansion or, contraction here, contraction here. So we're not given the, the strain to reduce that area. What about the stress in 3, 3? Can we calculate that? Yes, because it says we exert a force of 784 newtons. The square seat has an area that's side length of 23 inches with 1 inch equals 0.025 meter. So I could define my cross-sectional area, A. A is just going to be equal to, for a square, 20, or for a cube, 20, or 23 inches, 23 times 0.0254 to convert that to meters squared. My force, F, is going to be equal to minus 784. I put the minus sign because, again, we're compression. So yeah, and then I know that my sig 33 is just going to be equal to F over A. So that's it. So I can figure out sig 33. Now I just need to write 3 equations to solve these 3 unknowns right here. So, and actually you'll see it gets a little, even a little bit more straightforward than that. So let's continue with defining. So now E11, so 1 over Y, what is kind of my expression in here? So I have to first, is there any stress in the 1, 1 direction? No. So there's no stress in the 1, 1 direction, no stress in the 2, 2 direction. So using our formula that we've derived previously, let me go way back into the lecture notes just to kind of remind people of our most important equation in mechanics, which is this expression right up here. Actually, it's a little bit down. Actually, sorry, it's further up, excuse me. This is our kind of key expression. So if I'm looking at E11, there's no stress in the 1, 1 direction. There's no stress here in the 1, 1 direction. There's no stress in the 2, 2 direction. It's just the stress in the 3, 3 direction. So going back to our problem, let me head back here. So there's no stress in the 1, 1 direction. There's no stress in the 2 direction. It's just going to be minus nu times my sig 3, 3. That's it. If I'm doing this 2, 2, same exact thing. It is going to be 1 over Y times Y times minus nu times sig 3, 3. And for E33, we know that it's going to be 1 over Y times sig 3, 3. Our only time that we're going to be able to use our Hooke's law. So that's it. So these are our expressions. I'm going to shift enter. Now if I look at my stress tensor matrix form, there's my values, calculate them out. Here's my strain, matrix form. That's it. Again, we could go to double check this. We know that these should be positive values. They're going to expand essentially in the same amount. And here we have our value for compression is negative. Excellent. So we've already answered right now the stress tensor for this problem quantitatively and the strain tensor. So now we're asked, what is the rotation required to be in the maximum principal normal stress state? Well, looking here, we're already in the maximum normal stress state. We only have normal stress contributions. What rotation is required to get maximum principal normal? What about maximum shear? So the maximum shear, again, if we're already in the principal normal stress state, we need to rotate a theta of 45 or 2 theta of 90, either clockwise or counterclockwise. So, yep, we've answered problem. What is the critical crack size required for the chair to fracture? And this is the critical crack size required for the chair to fracture given the load that we're applying, or the stress that we're applying. So that is just Dwight simply sitting on the chair and having it fracture. So we're trying to figure out, for that given stress, sigma 3,3, what's the critical crack size required for a fracture? So if we look up here, we have these 3 equations for how to figure out our critical crack size. So Griffith, Orwan, fracture toughness. Now, we shouldn't want to use Griffith anyways because we're not dealing with brittle materials or glasses. Instead, we want to use probably Orwan or fracture toughness. But let's see what we're given this problem that we can actually solve. So are we given the surface tension or the surface energy? No. Are we given G sub C? No. We're only given fracture toughness, which is this value right here. So let's go ahead and solve for this expression. So our fracture toughness is 29 times 10 to the 6. Pascals. This is going to be equal to Mathematica for the solve doesn't like those negative values, so I'm going to do this. Again, it doesn't really matter. Square root of pi times a sub c, because that is our critical parameter, a sub c. So our critical crack size required to make this material fracture is 5 times 10 to the 7th meters. So ridiculous. Basically, this material, given this stress, will eventually never crack. But again, that's our parameter. That is our a sub c. Is equal to, I'm just going to copy it here. That is in meters. That's it. So we've answered that this question. Now comes to the hard part. Dwight is convinced that Jim created an initial crack in his chair that was 0.1 millimeters long. So we have an initial crack length. I'll move this over here. Initial crack length, A naught, which is equal to 0.1 times 10 to the minus 3. That is our initial crack length. Knowing that after sitting and standing up in his chair for 55,000 times, it would break. So that's Dwight. Was what Dwight is thinking. Is that Jim created an initial crack length, knowing that fatigue it would eventually break after that 55,000th time. So we're going to see, is Dwight correct? Does his analysis hold true? So first it asks, what is R here? So R, remember, is our ratio for fatigue. It's your ratio of your sigma min minus your sigma max. So what is our sigma min here? So our loading state, or our kind of stress state, our cyclical cycle. So our stress, this is 0. So this is my 0 value for stress here. This is time. So what Dwight is thinking is that Jim set up his chair. So initially there's no load, and then I compress. So I compress my chair. I stand up, go back to 0. I compress my chair, so it's this kind of step function here over and over again. So what is sigma max? So my maximum stress is 0, right? The unloaded state. My sigma min is going to be my sigma 3,3 because it's negative in compression. So R is equal to sigma min divided by sigma max. So my R value here is infinite. So that is kind of your R value for kind of this fatigue cycle behavior. So here M is equal to 4, C is equal to 10 to the minus 10. Shear modulus is this, UTS is this. I'm just giving fake information to kind of throw people off the scent here. So let's define, again, we're dealing with fatigue, so we know we're going to have to use, we need to calculate our number of cycles to failure, given we know this critical crack size here and this A naught value here. We want to calculate what is that number of cycles to failure. And then see if that's true, if Dwight is correct, if he thinks that it's going to fail at 55,000 times. So I know that my C is equal to 10 times 10 to the minus 10. My M is equal to 4. And now my NF is just going to be this unfortunately awful expression. So 1 divided by C times del sig. So del sig, remember, is just your the change. So this is, we had in our expression for this del sigma, and that is sigma max minus sigma min. So that goes back to your kind of Paris law here. So that is going to be, that sigma is the change essentially in your kind of stress. So it's that that kind of amplitude, the stress amplitude there. So your del sig in this equation, I'm just going to rewrite it, is going to be this sigma 1. It's going to be sig 33. So it's del sig times right here. This is going to be times your square root of pi, and then all of this to the m power. Close that up, and then now it's going to be a sub c to the 1 minus m divided by 2. Again, this is all in the lecture notes and in the OER posted online, and we've gone through it in another video as well. You worked on it in the problem set. So if we have already this code available, so you could just switch and plug in and adjust parameters. So this might, oh, I think I'm missing a parenthesis somewhere. And this is essentially my value. So here I've got my a sub c, I've got my a naught, and I can see that this is very, very different in terms of my number of cycles to failure. So my number of cycles to failure is much, much, much larger than 55,000. So Jim did not trick Dwight. So something else funky is going on here. So yeah, that's pretty much all we're going to have to deal with in here. So that's everything. So that's the end of exam 2. Again, we can practice more. If you have any questions, please let me know, and I'll see you all at the review session. Thanks. Bye.